Hi guys, so I kind of messed up last week when I was in the order of the actual lecture. So it turned out that the lecture I wanted to actually do first was not the one I actually showed, but this is the one I showed the previous week, which I really wanted to show, not this one, but actually I wanted to show you guys this lecture. All right, so I had meant to first introduce a sampling distribution and elucidate the central limit theorem. So you can see from the actual slide that this lecture should have followed the normal distribution, but instead I jumped to this one by mistake. So you will actually see, so I jumped to this one by mistake, which doesn't make any sense because you see we didn't cover the topics here just yet. We hadn't covered this. So what you will actually see, you will see that week 9, lecture 1 is actually going to be a lecture we covered on Tuesday. So I realized that I taught it out of order. I apologize. So what I've done is I've recorded the lectures in the order they should be, really because I realized next week we're going to be doing a lot of midterm review anyway. So it may be the case that we don't actually have a full lecture next Thursday because that's the midterm. So I figured I would use the time to catch up in the way I was supposed to because I taught out of order. So like I said, week 9, lecture 1, you're going to see is going to correspond to Tuesday's lecture because I made a mistake and taught it out of order, which means that if you look at the content for week 9, you're going to see that the PDF has been updated. So this means that the slides that I taught on June 29th is now July 6th. So if you look at the slides, you're going to see you've seen them before in the previous week. I moved them to the appropriate week. And I'm now introduced a new set of slides that was supposed to be taught this week. I'm going to, make them available now. This is the slides you should have seen this week. This is June 29th content that I accidentally taught out of order. So now this is the new set of slides. I'm going to make an announcement about that, right? So you can see that I hadn't taught you guys what a sampling distribution was. So if you watch Tuesday's lecture, some parts may be unclear and fuzzy because you hadn't learned the stuff you're supposed to learn just yet. So I had to change the order. So now you're going to see new recordings for week 8, which is this current week, because the order, I need to change the order. I taught out of order. And then because of that, the quiz, I will think about how to do that because that means you didn't see the material at all in class. So I may have to do something about the quiz. We could probably discuss this as a class as to what seems best for people, merely because, I'm going to record this week's content now, so you wouldn't have had enough time if you think about it. It's really just the concepts because you're studying for your midterm right now. So I'll think about what to do about that. So we find a solution that's equitable because I made a mistake in teaching the order in the wrong way. So I can't penalize people for that. So I need to think about a way that makes it still on target for the course content, but that people don't feel like they've been shortchanged to study time because I permuted the order of the actual content. So yeah, what you should have seen on Tuesday was is this basically. So notice that you can see that the previous week was actually the normal distribution, which is week 6 content. So this was the content we saw previous to the reading week. Right, so this is the content we should have seen after the reading week. So this is this week's content. So we're supposed to introduce the sampling distribution and the distinction between sample data and sample data distributions, because it's not the same, right? So sampling distributions versus sample data distributions not the same. I want to elucidate this, which I didn't elucidate this week because I can't taught it up order. I apologize, guys. So I want to motivate what the heck a sampling distribution is, right? So first of all, let's consider smokers. So if you look at the next week's content, which will actually be what we originally taught this Tuesday, you'll see that I start off with the hypothetical smokers example, which I didn't give the motivation as to where the example was coming from because I had really meant to introduce what happens if you have a sample, if you have a population of size big N when you keep extracting different samples of size small n, like has that changed the actual estimator of theta? So if theta is your actual estimator, if theta is your actual thing you want to estimate, if you take different samples of size little n, how does that change the estimator itself? But that's what I really want to elucidate when I talk about sampling distributions. So I'm going to talk about those things, right? So example 1, again, hypothetical population of smokers. So let's suppose we have a very, very finite sample or population of size 4. So this is incredibly finite. So finite, it's almost contrived, but it doesn't lend a hand for illustration because it's so small. I can kind of manipulate different samples of size 2. I'll show you how it's working. So let's suppose we have a population of size 4. And let's call those people A, B, C, and D. Now, 2 of those people are actually smokers. And I think in the example, I have person A and D as smokers. Yeah, so consider, for instance, A and D are smokers, B and C do not. Now I want to calculate the number of smokers. And if I tell you, okay, you tell me the exact proportion of smokers, you're going to say, well, intuitively, there are 4 people in the population, right? And 2 of them are smokers. This means that theta is equal to a half, basically, and you'd be correct. Now you can calculate this value because your population is so finite, you know well the players are, and it's possible to compute theta. In practice, you can't because the population is incredibly big. And while it's still finite, it's finite in a way that's it's almost infinite. So if you have like a 2 million people, that's finite, but it's in a very large way. So you cannot tangibly compute theta, right? Now, we have theta as a parameter that characterizes the proportion of people who actually smoke. Okay. Now, what is a sample? A sample is always a smaller subset of the population. So let's suppose we have person A, B, C, and D. Well, if I want, this is my population, a sample is always a smaller set. So if I pick person A and D, this is a sample of size 2. It is, so notice that the sample is always less than the population. It's always necessarily less than the population. That makes sense because you have less people in your sample than you have in the population, basically, right? Okay, so now let's think about how we can use this to motivate why we have this notion of a sampling distribution. And how does a sampling distribution differ from a sample data distribution, right? So a sample, recall, is a set of data that is collected from a defined population. Now, it is collected from a population. So you first have to identify the population you're interested in actually sampling. And then your sample is a subset of that, basically. Right? Now, the issue with the sample, and the reason we care about it so much is that even if you sample in an unbiased way, so let's suppose we use some random sample, you're not necessarily guaranteed to get the same sample each time you take a different random sample. In fact, you're probably most likely going to yield a different sample a lot of the times, right? So in this schema here, you can see that I have a population of size 12. I want to take a sample of size 2. The first time I sampled, I extracted person 2 and 5. The second time I sampled, I extracted person 8 and 10. Now notice that I have extracted 2 different samples of size 2 from a population of size 12. Unfortunately, because you have different units in the 2 different samples, any inference you make about the true population theta that exists over all 12 subjects is going to look different between the 2 different samples because you're making an inference on different sampling units. They're going to yield different estimates, right? So for instance, if the thing I want to estimate is the average height of those 12 students, well, the sample 1 would say take an average of the height of person 2 and 5. Sample 2 will say take an average of the height of person 8 and 10, but person 2 and 5 are not the same as person 8 and 10. They're not guaranteed to have the same heights. You may get very different estimators of the heights at the population level because you yielded different samples. Now, there's going to be an error based on this because you sample in such a way that you obtained different samples of size n, basically. So there's an error that comes from the fact that each time you take a different sample, you're not going to get the same estimate, basically. Right, so let's go back to our example to really illustrate this. So remember, our population is size 4. Now we're taking a sample of size 2, right? How many different ways can we actually get a sample of size 2 from a population size 4? There are 6 different ways. And I've literally listed all the permutations for you guys. So you can extract person A and B. You can extract B and C, A and C, A and D, B and D, and C and D, right? So you can get 6 different possible permutations of your sample of size 2 from, and I should say 6 different unique permutations, because of course B and A, so 6 different unique permutations, right? Because of course it's the case that AB is a different permutation of BA. So what this says is that in the first sample, you got person A first, and then you got person B. The second time you did your sample, you got person B first, and then you got person A. So these are different permutations of sample of size 2, but we recognize these are the exact same samples because the permutation may be different, but the people in the actual sample are the same. So there are 6 different unique permutations of size for a sample of size 4. Now, because person A and D are the smokers, depending on who you get in your sample, you may get all the smokers in your sample, or you may get none of the smokers. And in either of those extremes, that doesn't reflect what you saw at the population level. So we know half of them are smokers, half are not. But if your sample contains all the smokers, it will tell you your data is 1. If your sample contains none of the smokers, it will tell you data is 0. And that doesn't reflect what you saw at the population level. See, sometimes the way in which you sample may yield an estimate that doesn't make sense, right? So your estimate can be kind of off in some sense, but it can't happen too often, basically, because if your sample is truly actually unbiased, most of the time the theta hat for that particular sample is going to be close to theta. Let's see why this is true, right? Now recall that a statistic is a numerical value that characterizes the sample, right? So that means you have a set of observations, and then from that set of observations, you computed your statistic, right? So that means that I'm going to do the exact same thing that I did with the population thing, where I had a sample size 4, except this time, sorry, but I had a population of size 4, except this time the sample is actually size 2, right? So let's see how this is going to work. So let's see. So, okay, so I have a sample. So let's do, and so I have 6 different samples, which means I define an estimator for, that's why you see 6 theta hats, right? So now remember, sample 1 is person A and B, I think. Yeah, so A and B. So we have A and B, right? So then because we are only taking a sample of size 2, so this is, the absolute value of A and B. So I'm trying to take the size of the thing is 2. Right? So when I do this bar here, it means size. So this is me saying the size. You need to know that. Just me being a bit, you can see from here it's 2. I think like a mathematician, so I'm always thinking about how to make it precise, but you can see it's 2 here. Anyway, so the denominator is 2. Right, so because there's 2 people. Now recall that A and D are smokers. So this means that by definition, B and C are not. So A is a smoker, B is not. 1/2. This yields an estimate that is the same as the true value, because remember the true proportion of smokers is right? Now, here's the thing. We can play that game because the second sample is, A and C, which is another sample of size 2. So this means that, you have the theta2 hat is equal to 1/2 because C is not a smoker. You're going to keep doing that, but the first instance where you get something that's funny is with the third sample, because sample 3 is A and D, but those are the smokers, right? So if you look at N3, you get person A and D, and so you get 2 out of 2 are the smokers. It will tell you that your estimator is going to be 1. It's estimating that everyone is a smoker, right? Similarly, the next time it gets something also that's funny is when you're getting to group B and C. So sample 4 is also funny because it is persons B and C who are not the smoker. So when you look at, that's N4. When you look at the issue is that when you look at, theta4 hat, you're going to get 0 out of 2. It's going to tell you that no one's a smoker, which is equally bad, right? So you're going to get some funny instances where your estimator is very bad, really because even though you sampled in an unbiased way, you happen to get a non-representative sample, right? So you can sample unbiasedly and still get a sample that is not representative of the population, because if your sample has everyone is a smoker or no one is a smoker, certainly it's not representative, right? So this is something we have to, this is just what it is basically, right? So let's keep in mind that each time you get a different sample from the population, your estimator is going to change basically. Sometimes the estimator is good. Most of the time it's actually good. So most of the time it was actually kind of good. Oh, not that one. So you can see that 4 out of the 6 times, it's pretty good, right? So there are these 2 middle instances here where it's kind of not great, but that doesn't happen too often, right? So 4 out of 6 times is pretty good. Now, again, there's a portion of the time when even if you sample in an unbiased way, you get a sample that is not representative. And that happened in this example here twice. When you got everyone was a smoker and no one was a smoker, you got a sample that was not representative, right? Now, in reality, we can't check that. You see, we were able to directly check how many times we were off. We noticed that we were off 2 out of 6 times it was off. In practice, we can't do that because N is much larger than 4. In reality, we don't have access to all members of the population. So the truth of the matter is we can't even do that in reality, basically, right? So we can't do that in reality. So this means that it is in some sense kind of hard to know how off you are basically, but this is the reason why we're going towards the center limit theorem basically, because even if we can't actually literally realize, even if we cannot realize every possible sample of size N, as if we could realize every single possible sample of size 2 in this example here because it's small size, we can't do it in practice. If we put a distribution on our random variable, if we put a distribution on our estimator, and by saying if we put a distribution on our estimator, I mean that if we're for instance estimating the mean, or in this example, if we're estimating the actual proportion, if we put a distribution on theta hat, so that it has some distribution, even if we can't realize every single possible outcome, we can still determine the probability of observing some observations. And in practice, observations, we get things like this, where it says there's a 1% chance, 100% chance of a smoker, or a 0% chance, should have low frequency because it's unlikely. So even if we cannot realize every single possible sample of size n to compute all the possible ways you can get estimators for theta hat, we can still put a distribution on our estimator, theta hat, and determine the probability of seeing a particular, theta that is unusual. And we would say the odds of seeing a particular theta, like this one or this one, is very low. So we would probably put more the probability on the ones where it says a half, basically, right? So let's see how this is working, basically, right? Let's compute it. And I want to see how far it takes us to do it. So yeah, I'm going to compute it here for you guys, but that's a to be continued. So I'm going to compute the distribution. So you can see that it's going to put most of the probability on the very likely outcome space. And it's going to put very low probability on the ones that are not very common, right? Okay. Let's recall something basically. A random variable or event is one in which you cannot anticipate the outcome. When the event happens, you don't know where it's going to land, but there's a probability of each particular outcome, right? That is not necessarily equal across each particular outcome. So roll a fair die, the probability of getting 1, 2, 3, and 4, or 5 is equal in that outcome there, but it doesn't have to be, right? So you can have a random variable where the probability of getting a particular outcome, like heads or tails, is the same, or flip a fair die, but it doesn't have to be, right? Any random event or experiment is just something where the outcome is not known before it happens, and there's a probability on each of the possible outcomes of that process, right? So flip a fair coin, there's 2 possible outcomes, and there's a probability on each of those outcomes, right? So even the proportion of smokers is a random variable because, the proportion of smokers being like, we have 6 possible realizations here of theta. So we have all these possible thetas. And the reason why it's random is because each time we get a different sample of size 2, the proportion of smokers is changing. So whenever you have a change in the outcome that is happening because of a random process, so the random process is the changing of the sample size. Sorry, not the sample size, the changing of the sample itself. So because the sample changes from like AV to AC, etc., it's a random process because each time you're going to get a different estimate for theta hat, basically. Sometimes the estimates will be the same, sometimes not, right? So again, the report theta hat is a random variable because the particular sampling units you extract are changing each time you do a simple random sample. And therefore, theta hat is going to change for each of the samples, right? Now, this makes it a random process, basically, right? As in, like, you cannot predict the outcome before it happens. Right? We don't know if we're going to get person A or B. We don't know if we're going to get person A, B, C, or D in our sample before we actually see the sample itself. And so we cannot anticipate what theta hat will be before our sample is drawn, right? So that's what we mean by random process, right? Yeah. Now, what is, so remember that when we talk about a frequency, or in some sense, a random variable, we want to compute the expectation. I'm going to leave this example here because I might use it again. We want to compute the expectation. We have expected value of x is equal to sum over all x. If x p of x equals x, I'm pretty sure I did this in the week 9 content, which you'll see in a bit, but anyways, looks like the same thing is coming up multiple times. You can actually see that you're not going to get, so this is a random variable, this is an outcome. The probability that x is equal to x1 does not necessarily equal the probability of x equals x2. Each of them have their own, not necessarily equal. They all have their own probability of their own frequency of occurring, right? So it is actually corresponding to the proportion of times the particular outcome occurs. So probability that x is equal to x1 is saying the proportion of times random variable x lands on little x1, right? Whereas this one is the proportion of times x lands on little x2, right? So this is changing. They don't have the same frequency basically. What we do know is that if you think about all the possible outcomes your random variable can take, the probability that x, the probability for each, that it has to sum up to one basis. The probability of each, so sum of all the possible, sum of overall x, of p of x equals x, it has to equal to 1. If you sum up all the possible outcomes, it has to equal 1 because of probability, right? So, again, remember the distribution is literally saying, listing all the possible outcomes as well as the proportion. So now let's look at how this is working basically. Recall that, again, for the proportion of smokers, we have the following. We had this. So we knew that, for instance, theta 1 hat was a half. Theta 2 hat is also a half because I think theta 2 hat was like A and C. But theta 3 hat was like A and D, which are both the smokers, so it was 1. Theta 4 hat had all the non-smokers, so it was 0. And then if you look at samples 5 and 6, so this is B and C and D. B is not a smoker, D is a smoker. C is not a smoker, D is a smoker. So they each have probability of a half. So it's 1/2, which is what you see here. All right, so the only possible outcomes for our proportion of smokers is it can either be 0, 1/2, or 1, right? So those are the only proportions it can take. Now, how many times is it equal to 0? What only happens, so there, first of all, there are 6 possible proportions. There, if you look at the thing here, there are 6 possible theta hats that we are estimating, but only once you get 0, which is here. So this is a too bad outcome from, even though you sampled in an unbiased way, you unfortunately yielded a non-representative sample. So that happened 2 times, right? So now we can say that only happened 1 out of 6 times. And then you can also say that the number of times you got 1, which is another bad outcome, is only 1 out of 6 possible trials, basically. But that's also 1/6, which means that it has to be the case of 4 out of 6 times you got a half, right? So notice that the distribution is saying that 1/2 is the most common observation. It's literally telling you that the mode of this distribution is going to be at where it should be, which is the half, because the half is a true parameter. So it makes sense that it's going to peak where it's supposed to, right? So this is what it's telling you basically. I just put that out there. It's going to peak where it's supposed to, which is at 1/2, because at this outcome 1/2 here. Because that's, we know that at the population parameter, it's a half. It's really 2 out of 4 are the non-smokers. Sorry, 2 out of 4 are the smokers. So it's a half in each camp. Okay. I notice that it puts lower mass, it puts lower probability in these unlikely events. These are unlikely events. It's telling you that the chance of seeing 0 or 1 is pretty low. So actually, if you compute the expected value of this, let's see what happens. So 0 is an outcome times 1/6 plus 1/2 is a possible outcome times 4/6 plus 1 times 1/6. So this is going to be 0, obviously. And then 4/12 plus 1/6 times 2 is going to be equal to 6/12, right? So we're just going to do the following. So yeah, again, 4/12. I'm going to multiply them together, plus 2/12 is 6/12, which is a half. Look what happened. On average, it's telling you that this particular theta is sitting at a half. More on this in a bit. So it's literally telling you that on average, right? Theta hat sits at a half, which is good. How come? Because the actual population parameter is actually a half. This is not a coincidence, by the way. This is literally telling you that it's literally telling you that this particular estimator is unbiased, right? So this it's actually saying this is unbiased. Because on average, it peaks at the population parameter, which is where it's supposed to be, basically. That's great. Like, hooray. Like, turns out the expected value of our random variable x is going to theta, which is what we want, basically, right? So there's more on that in a bit, right? So this is good. And this is what I actually showed you guys on Tuesday when I should have waited. So I should have showed this first, but anyways. This is good because it gives us a way to have confidence in the idea that even if sometimes we messed up, so by mess up, I mean, sometimes we land here or we land at 0 proportion. Most of the time we sit where we're supposed to, which is at a half. That's a good thing. An estimator is good if on average it sits where it should be. So you could have fringe case where, sometimes it didn't land where it should. Most of the time it should land where it should be, right? So here's me just giving you an example to how I got the distribution above, but I've also worked it out here. So I've worked it out here as well, but here I was just saying that we know there are 6 possible outcomes because there are 6 theta hats, because there are 6 groups. And then we know that it's a half for samples 1, 2, 5, and 6, whereas 3 and 4, I think it was like 1 and 0 respectively. This means 4 out of the 6. So obviously, if they're all equal outcomes, then 4 out of 6 times it corresponds to this. Then of course, probably the theta hat is equal to, let's say, 1.0. It was 1/6, and we know that was also equal to probability that like theta hat is equal to 0.0. Right? This is the most common outcome was when it was a half. Okay. So from above, you can see that we use the statistics from the sample. What do I mean by that? I mean that we used the statistics from each of the 6 different samples. There were 6 samples. And each have a theta hat. Each hat, we use those statistics to find the distribution. So this is a distribution on theta. This is the distribution on theta, which is distribution of theta hat, which we found using each of the 6 different estimates at each of the different sample statistics from the different samples, right? Now, of course, we can make this study even bigger. We could, of course, make, for instance, we could make our instead, for instance, we had a sample, if for instance, that instead we had like a population of size 1,000 or something, and we took a sample of size, we take many different samples of size 150, we can fine tune our estimates, obviously, right? So if, for instance, like I said, if we increase our sample to 1,000, let's suppose we have 1,000 people in the population and like 500 are smokers. So we have a portion of, again, like 50 people. Sorry, instead we have a portion of half who are smokers and half who are not. So that means in this case, 500 would be smokers, 500 would not be. We can take different samples of size 150 and then put another distribution on that, basically. Right, so we could obviously keep taking bigger samples and bigger populations and making more distributions that look like we did here, right? And the question is, if we keep taking different samples of size n and make them incredibly big, what happens to the shape of the distribution basically, right? I claim that if we keep taking our sample size to be bigger, the shape will be normal with a mean at a half and a smaller standard deviation, right? So you might say, how did you know to do this, right? So to be continued, right? So how do I get the standard deviation of like 0.02 to be continued? So again, I claim that if I make my sample size bigger, the distribution will look normal. And that is the central limit theorem, which I'm going to elucidate to you guys very soon. With a certain standard deviation that comes from the normal distribution itself. This part is a to be continued. Right, so this part here, why is it the case that this is the standard deviation? That's a to be continued. However, I will say the reason why this mean is 50 is because of the reason we had here. That the expected value of your theta hat will converge to a half basically, right? Because you know the true theta is a half. We take the expected value of all your possible outcomes for theta, it will converge to where it should be, which is the true population parameter of you know, like a half. That's if your sample is truly unbiased. You sample in an unbiased way, you didn't sample in a way that's not unbiased. Right? So I'm going to take this opportunity to say that recall that we do care about sample size merely because, first of all, when your sample size is big, we can then claim that the distribution on your estimator is going to be normal. That is a central limit theorem. I'm going to introduce very soon. We don't have any such guarantee about normality for smaller sample sizes. And the problem is that if you don't have a normal distribution, you cannot talk about confidence intervals. And we do care about interval estimation. So we cannot talk about margin of error and interval estimation if we don't have something that looks symmetric. This is why we care about the sample size, right? So notice that when your sample size is only 10, you have no guarantee that it looks, you know, at all symmetric. In fact, this looks slightly right skewed in the first sample size 10. When your sample size is 100, you get some kind of guarantee that it looks normal. And actually, I would claim that sample size, a guarantee of normality, actually happens at a sample size of less than 100. But to be continued. When you have a sample of 1,000, notice that your actual is still normal, but notice how it actually becomes more precise. You see that even though this is normal here, notice that it's going from 9 to 12, whereas here it goes from 10 to 11. So it's actually condensing. It's getting more compressed as you increase your sample size. So even though it's normal at a smaller sample, it becomes more precise. The interval on the estimation becomes more precise if you increase your sample size. So you get both precision as well as you get central limit theorem from a sample size from a sample size framework, as well as precision. Like the precision of your actual estimator becomes more and more narrow with an increased sample size, and you get the central limit theorem. Right. So I'm going to pause the first week's lecture here and then continue with the second portion in a different video because it's easier to break it up so you don't feel like you're watching too much at once. And then when we get back to the next video, we will start with how I got that number that I did. Like, how did I get, how did I actually get that 0.02 basically, right? And if it's 0.02, what does that mean for the margin of error basically? So you can see I'm going to compute a margin of error, which is a confidence interval, under the stipulation that when distribution is normal, because then I can use the empirical rule, which I should not unless I have this normality. So we're going to stop here and then continue with this after break for me, because you're not watching until you see the video recorded, but my break basically.